So now we take up the final example in the canonical ensemble. And this corresponds to what is called a classical solid. We have looked at it in the microcanonical ensemble, and I have n oscillators which are essentially lying on a one-dimensional lattice, and they are being confined by a harmonic trap. So that the Hamiltonian is given by pi square over twice m plus sum over I half m omega square qi square. Now this, as we have said before, is in 1D, one-dimensional space. The generalization to higher dimension is not a very complicated problem. So the Hamiltonian I can write down as sum over I hi. So this is a non-interacting system, and consequently I can write down the Hamiltonian as sum of single particle Hamiltonians, where hi is pi square over twice m plus half m omega square qi square. The n particle partition function is dp1, dp2, dpn, dq1 to dqn e to the power minus beta h bar, which becomes dp1, dp2 all the way to dpn, and you have dq1 to dqn e to the power minus beta sum over I pi square over twice m plus beta by 2 sum over I m omega square qi square. Now clearly this sum, if I write down explicitly, becomes product of exponentials, so that I have minus beta p1 square over twice m e to the power minus beta p2 square over twice m, and then I have minus beta pn square over twice m. I have eta beta by 2 m omega square q1 square, and then finally I have beta by 2 m omega square qn square. So hence I have dp1 e to the power minus beta p1 square over twice m. But before we proceed, one has to be careful, because this quantity is dimensionless. This quantity is dimensionless because the Helmholtz free energy is going to use log of this partition function, but this measure is not, right? So that I have h to the power n that must come and sit over here. So let's now group the terms together. I have dp1 dq1 over h e to the power minus beta p1 square over 2m e to the power minus beta by 2 m omega square q1 square. Then I have dp2 dq2 over h e to the power minus beta p2 square over 2m e to the power minus beta by 2 m omega square q2 square, so on and so forth, all the way finally when I have dpn qn over h e to the power minus beta pn square over twice m e to the power minus beta by 2 m omega square qn square. I want to compactify my notation, so that essentially I will write this as product over I dpi dqi over h e to the power minus beta pi square over twice m, and then I have minus beta by 2 m omega square qi square. Now this integral that you see is a Gaussian integral, and effectively in the earlier equation you can see that this is a product of n Gaussian integrals, where I write down I as dp 1 over h dp dq e to the power minus beta p square over twice m e to the power minus beta by 2 m omega square q square. And all of this integral is going to give me I, and all the way over high. And if you see that this is nothing but the single particle partition function q. So this is the single particle partition function, and the n particle partition function would be q to the power n. Here again I do not have a n factorial. Why? Because essentially I mean I can distinguish the particles by their mean position. So let's evaluate this integral. Let's evaluate q is 1 over h dp dq e to the power minus beta p square over twice m e to the power minus beta by 2 m omega square q square, which is going to be, I can separate out the integrals, minus beta p square over twice m dq minus beta by 2 m omega square q square. I use the integral, the Gaussian integral minus ax square is going to be pi by a square root of that, so that the first term is going to be square root of pi over twice m by beta, and the second integral is going to be pi divided by beta m omega square times 2. So if I bring everything together, then I have 2 pi times m beta, and I have 2 pi times beta m omega square, and then essentially I have raised to the power half, which gives me 1 over h 2 pi whole square beta square omega square, and that is essentially raised to the power half, and that you are going to get as 1 over h 2 pi over beta omega. But this answer is very familiar because h over 2 pi is h bar, so that I have kBt over h bar omega. Hence the n particle partition function Zn becomes kBt over h bar omega raised to the power n. It's dimensionless because you see kBt has the dimension of energy, and so does h bar omega. The Helmholtz free energy is minus kBt ln of Zn, which is, if I use this expression for Zn, becomes minus n kBt ln kBt over h bar omega. Now one can determine the entropy from this relation. How do you determine the entropy? Well, we know the root. F is U minus Ts, and I have to figure out what U is going to be, and therefore this would imply that Ts is going to be F minus U. Am I right? U minus F is going to be U minus F is going to be Ts, right? As we have seen, the average energy which we identified with U, so U is equal to the average energy of the system, which was sum over E in the canonical ensemble minus beta E 1 over Z, and this means that I can rewrite this expression as del del beta of e to the power minus beta e with a minus sign, which means I have minus 1 over z del beta of sum over e to the power minus beta e, and this quantity is the partition function that we are looking for. So I have minus 1 over z del beta of z, which is minus del beta of ln of z. Ln of z in our case is nkbt ln kbt over h bar omega. No, there is no kbt factor, I'm sorry. It's just going to be n times ln of this, which I will write down, since I have a derivative with respect to beta, I'm going to write down as ln 1 over beta h bar omega, which is minus n ln beta h bar omega. Now this gives me a del beta of this ln z gives me minus n over beta h bar omega times h bar omega, which is minus of n over beta. And this implies that u is going to be minus del beta of ln z, which is going to be nkbt, the result which we obtained in the microcanonical ensemble also. Now Ts then becomes u minus f, so that I have this is as nkbt, and f was minus nkbt, so that this becomes nkbt ln of kbt over h bar omega. Clearly I can take nkbt outside, so that Ts becomes nkbt 1 plus ln kbt over h bar omega. And this, you see, is going to be, this implies that the entropy is nkb 1 plus ln of kbt divided by h bar omega. Now I look at this expression that I have over here. Kbt is u over n, so that this expression implies that S is going to be nkb 1 plus log of u over n h bar omega, which means I can write down this as nkb ln of u times e, where ln e is going to be 1 divided by n h bar omega. And this is the expression that we have derived in the microcanonical ensemble from the total number of microstates. So everything fits like a jigsaw puzzle. With this, we come to the end of canonical ensemble, and next we are going to look at a different canonical ensemble, which is essentially where you allow fluctuations in particle number as well as energy.